Section 10 of the Western Boundary and Other Essays by Helmuth von Moltke, translated by Charles Flint McClumpher. This LibriVox recording is in the public domain. Read by Alistair. Considerations in the Choice of Railway Routes. Part 1. Many wise men believe that the railways, which so universally attract attention today, are a symptom of the sickly unrest and nervous impatience of our times, which are not able to do anything fast enough. Others regard them as a necessary evil, unavoidable, as was the introduction of the spinning machine among us, after that our neighbour had introduced it. The more general belief is, however, that these new means of communication, for which such great sacrifices have been made, and still greater will be, will somewhat satisfy the actually existing desire for the union of things intellectual and material. He who recalls the condition of all kinds of communication in his youth might well believe that the age of Methuselah has now been reached by him, when he views the present condition of the same. And yet it was only 30 years ago when we ourselves were swallowed up in the bottomless sand or deep clay roads before the gates of the principal cities. A trip from Berlin to Potsdam required the preparation of a journey. Frankfurt on the Oder was 2 days distant from Berlin. One took leave of his friends and equipped himself for all the inconveniences of bad storms, poor night lodgings, and overtimed carriages. Droves of horses panted with their burdens over steep mountains and through deep valleys, over dangerous stone piers, with most lucky mishaps, and everywhere pavillage, bridge tax, and passage money were levied. The highways of the Middle Ages were almost unchanged until our time, except that the robber knights were supplanted by the legitimate waylaying of the toll gates. After the long bloody battles inherited by our century from the preceding one had ended, a complete revolution of the avenues of communication took place. Since the Treaty of Paris, the energy of nations has passed from destruction to creation in every respect, and more has been done for ways of communication in the past 30 years than in the 3 centuries preceding. A net of highways between all the more important points has been made, and in Germany alone the total mileage of artificial roads constructed during this period amounts to 1/2 of the earth's circumference. Yet the paved roads alone were not sufficient for the industry which had sprung up and continued to develop more strongly, and the invention of the locomotive and railroads now first made it possible to meet the demands of the new state of affairs. Although this invention of our days greatly busies the minds of men, yet it may be affirmed that a knowledge of the properties of the same is by no means generally spread abroad. Not that there is need of excellent works upon this subject. They are, however, for the most part comprehensible to the technologist alone, just as generally popular interpretations follow after science has made the way. Footnote: so far as we know, there existed in 1842 neither a popular treatise upon railways nor a technical work upon their construction and management. Streckert. End footnote. Therefore, before we discuss the particular object of our investigation, it would not be amiss to collect a few technical details so that they will be comprehensible and clear to the layman. It is well known that the railway is a way, with tracks of strong cast-iron rails, which, with the slightest possible deviation from the straight line, horizontally and vertically, that is, by the shortest route, and with as little ascent and descent as possible, are laid between the points to be joined. Footnote: cast-iron rails, 3 feet or more long, were laid as longitudinal sleepers in the surface construction of the first English railways, and afterwards in the construction of horizontal sleepers until the middle of the year 1840. The first wrought-iron rails, 15 feet long, and in the present usual form, were rolled in the year 1828 at a foundry near Durham. Streckert. End footnote. To answer these conditions, the railway will sometimes be cut through elevations as a narrow pass, sometimes pierce through them as a tunnel. At times it must stride over the valleys as a pier, bridge, or viaduct. But often it has to pass around in gentle curves where such surface difficulties cannot be overcome. After that the plan or surface of the way has been laid out, so that it corresponds as much as possible to the conditions just mentioned. The rails, which must be exactly parallel to each other, are carefully fastened on stone supports, oftener on heavy wooden beams, by means of cast iron supporters, or now mostly with headed spikes. The usual form of the rail resembles in a cross-section the figure of a T, over whose upper surface the wheels run. Its weight amounts to 14, 20, even 24 pounds for the running foot. Its length averages 15 feet. As it is well known that metal expands with altogether irresistible force at every increase of temperature, it is necessary to leave a short space of about 1/8 of an inch between every two rails. Because, as we just said, the iron track is not sunk in an indenture, as is the ordinary road, but is elevated, it is necessary for the wheels of the carriage which are to move over the same to be provided with a small edge or tram on the inner surface, so that they cannot run off this rail. One other peculiarity of these iron wheels is that they do not revolve on their axles, as is the case with wagons, but since it is necessary to keep their gauge very exact, they sit fast upon the axles, and revolve simultaneously with them in the pedestals which are fastened under the carriages. In order to make as much room as possible, the carriage top is made much wider than the trackway. For this purpose the box is placed over the wheels, not, as usually, between them, and therefore, to avoid the danger of upsetting, the wheels have to be built much lower than on ordinary vehicles, although large wheels would be a great advantage for railways also. They have tried to gain this advantage on a new English railway by increasing the width between the rails. Footnote: the width on several English lines, for example, the Great Western, is 2.135 metres, 7 English feet, while on the continent, with the exception of Russia and Spain, the normal width of 1.435 metres has been almost generally employed. Strecket. End footnote. The wheels could then be built higher without risk, and of course, a much greater speed was attained. But other technical difficulties, not in order of discussion here, were met with, which caused the continental roads to keep their usual width of track. It is obvious that a carriage on a railway will be moved far more easily than on an ordinary roadway. The load which is drawn on a railway by one horse at the rapidity of 2/3 of a mile per hour requires for the same speed on a granite track, like that of the commercial road in London, or those in upper Italian cities, 4 horses, on a highway from 8 to 16, on ordinary country roads, 33 to 66. A whole row of heavily laden carriages are joined, therefore, on the railway, and in front of this train is attached one black magic horse, snorting out steam and belching out fire, called the locomotive, the nature of which we shall examine somewhat more closely. Certainly it is not our intention to give in detail the description of a machine so complicated as that of a locomotive, that triumph of human invention, but the essentials and generalities may be touched upon in this essay. Between the wheels and upon the springs there is placed a water tank of wrought iron, firmly constructed. It is called the boiler, almost like the form of a reclining cylinder, and takes up nearly the entire length of the carriage. At its rear, and almost surrounded by water, is the firebox, in which a great fire is kept, from which the heat is conducted by means of a system of brass tubes, 40 or 50 in number, in order to make the greatest possible surface of contact through the water to a chimney standing on the fore end of the locomotive. After that, the water which has been pumped into the boiler to a certain height, and has been brought to the boiling point, steam is generated upon whose elasticity depends the operation of all steam engines. Steam's expansiveness increases with the height of the temperature by which it is generated, and the steam enclosed within the walls of the boiler will, if it continues to expand, finally burst the boiler, though it be very firmly made, unless an opening has been provided for it, as soon as its expansion reaches a certain degree. Now this is done in case of the locomotive, either by means of the cylinder when the machine is in operation, or by the safety valve when it is at rest. Steam is said to have an expansive power of 40, 50, 60 pounds, in case the force with which it presses upon the sides of the boiler from within is equal to 40, 50, 60 pounds of weight on every square inch of the boiler's surface. If one imagines, for example, that a piece on top of the boiler 1 foot square is loose, then, with 60 pounds of expansion, the pressure on it must be 8,640 pounds to prevent it from being blown into the air by the steam. If now the joined plates of which a steam boiler is constructed endure only 60 pounds pressure, and actually no more, it is easily seen that a pressure exceeding this maximum limit would necessarily burst the boiler with a fearful explosion, for the steam confined in it would form under ordinary pressure a volume more than 400 times as great. There are, of course, openings in the steam boiler to prevent this, and their covers are pressed down by a weight equivalent to 60 pounds to the square inch, or, what is the same, they are held down by a spring proportionately strong. These are safety valves. As soon as the pressure within the boiler exceeds that resting on the valve, the latter is opened, and we see a white cloud rush upwards, which we usually call steam, though it is steam already compressed to water, for steam is invisible, like the atmosphere itself. The force with which this surplus of strength escapes, and which would suffice to gain the prize for the electromagnetic machine, now gives us an idea of the efficiency of the locomotive. As soon as enough steam has escaped through the safety valve to reduce the pressure to not more than 60 pounds, the valve sinks itself and closes the boiler. The cylinders in front on either side of the boiler form another way of escape for the steam. In the cylinder is a piston or ram that can be driven forwards or backwards. When, by means of a regulator, the steam is allowed to enter the front end of the cylinder by a certain passage, it drives the piston back with great force. But before the piston reaches the end of the cylinder, the passage through which the steam entered is closed by means of a simple and ingenious arrangement, and an escape for the same is opened, leading to the smokestack by which it passes out at once. Simultaneously, an opening in the rear end of the cylinder is unclosed, through which the steam from the boiler now slowly passes into the cylinder, but enters on the opposite side of the piston and drives it forward, until again the escape to the smokestack opens, and the steam again presses into the forward end. The piston is thus continuously and rapidly driven forwards and backwards. The entire apparatus of the steam carriage rests on 4, 6, or 8 wheels, and of these the driving wheels must be distinguished from the guiding wheels. The latter are smaller and serve only to bear the weight of the machine. The former, far greater in diameter, are intended to drive it forward. Footnote: the locomotive built by George Stephenson, which received the prize given for the best and most rapid machine on the Stockton-Darlington Railway, near Rainhill, on October 6, 1829, had 4 wheels. Strecket. End footnote. The pistons in the cylinders, of which we have just spoken, are joined by connecting rods to the driving wheels, so that each movement, once forward and once backward, of the former result in a complete revolution of the latter. Friction is produced whenever 2 bodies in immediate contact move over each other. It is this that obstructs motion in all machines, first lessening it, and finally stopping it altogether. Yet the use of locomotives for moving loads depends on this very same friction. The elasticity of the steam generated in the boiler drives the piston backwards and forwards in the cylinders, as we have seen, and this motion is next imparted to the driving wheels, which thus receive the power to revolve. Because they find resistance, generally called adhesion, on the iron rails on which they rest, and this prevents them from revolving unobstructed on their axles, they drive this axle forwards, that is, they roll forwards and then draw the load attached along with them. When locomotives were first placed on iron rails, the flanges or fellies of the wheels were provided with teeth which were made to fit into corresponding indentures in the rails. This was accompanied with great inconveniences, and it was a long time before it was believed that there was a great amount of friction between turning wheels and rails almost smooth, and that thousands of hundredweights could be moved by means of this useful friction, and that, too, up very steep grades. Footnote: in 1804, coal trains were run by machines on the ascents of the Merthyr-Tydfil line in South Wales by R. Trevithick, into the wheels of which were driven nails outside of the running surface of the rails, and the heads of these nails caught into the wooden longitudinal sleepers. In 1812, on the Middleton coal line, a train was moved by a locomotive built by Blenkinsop, by means of a rack lying along the line, and by cogwheels. Strecket. End footnote. The obstructive friction, on the other hand, is that which is found in cases of all wheels between the axles and the wheel caps, and, in a less degree, between the fellies and the rails. Finally, between the inner parts of the machine itself. This resistance increases proportionally to the weight which rests upon the axles. If the total resistances exceed the greatness of adhesion, the locomotive and carriages stop, and the driving wheels, grinding on the rails with a great amount of resistance, turn on their own axles. Many experiments have shown that the force necessary to overcome the resistance, and to set in motion a wheeled vehicle on a hard and level surface, is about equal to 1/300th the weight of the object to be moved. In other words, a hundredweight on a cord, passing over a roller, would move a wagon of about 300 hundredweight, not counting, of course, the stiffness of the cord and the friction of the roller. But as soon as the road ascends, and consequently the load to be moved is said to be increased, the power necessary to overcome the resistance must still be increased by new power. This is constant throughout, nor can any part of it be removed. It is the same for the worst field way and for the smoothest railway, the same for a steep and for a gentle ascent. If the road has to be conducted, for example, over a hill 20 feet high, the power required to draw the load up the said hill would be quite the same, whether it be necessary to ascend a grade of 1/300 or 1/1000, with the only difference that in this case the unequal amounts of power are employed for equal amounts of time, and of course, in the given case these amounts of power would be proportional to each amount of time, as 300 is to 1000. The sum total of all the amounts remains, however, the same, and is equivalent to the weight of the entire load to be moved. Let us imagine a stretch of railway with a 1/300 ascending grade, up which a load of 300 hundredweight is to be carried. We need first 1 hundredweight to overcome the friction, next 1/300 of the load, or a second 1 hundredweight to move the load, a total of 2 hundredweight, or twice the amount necessary to move it on a horizontal plane. Again, for the ascent of a grade of 1/150, there is a need for 1 hundredweight of power to overcome the friction, but for the moving of the load are needed 300/150, 2 hundredweight, hence a total of 3 hundredweight, or 3 times the amount necessary to move it on a horizontal surface. With a grade of 1/100, 4 times the amount, and with grades of 1/86 and 1/37, 4 1/2 and 9 times the power are required. Yet grades of the last kind are found on English lines, and are traversed by locomotives. If a locomotive drawing the greatest possible load with its greatest speed on a horizontal line, and with its greatest generation of steam, reaches the slightest gradient, although it sloped only at a rate of 1/1000, and if it is desired to travel further with the same speed and load, there is nothing to do but attach a second assistant locomotive. If time or power is lost by the ascension of steep slopes, the same, on the other hand, is regained to a certain degree by the descent of the same grade. The weight of the load also increases the speed of the same, as it overcomes the resistance of friction. On a grade of 1/224 up to 1/300, the weight of the load is equal to the friction. The carriages, therefore, will slowly roll down of themselves. If the incline is more gradual, gravitation in union with steam power assists in increasing the speed nonetheless, but only when the grade is considerably greater than 1/300 does this cease to be a favourable circumstance, because one cannot travel with less than 0 steam power, and because, in order to avoid a too rapid and dangerous descent, the wheels must be locked, which is harmful to both rails and carriage. It is obvious that, in the descent of a steep and smooth surface, which inclines at a rate of 1/300, a dangerous velocity must necessarily be acquired at last, provided the incline is very long. For according to the universal law of gravitation, the motion, though primarily slow, increases in velocity at every new division of time, and so on to infinity. But another obstacle simultaneously opposes this velocity, and the experiments recently made on the Liverpool-Manchester line and on the Grand Junction line have furnished data quite as important as they are astonishing. A long distance was taken, extending horizontally fully half a German mile, so that a train of 8 or 12 heavily loaded goods vans could be moved on it with a great velocity to the edge of a steep descent, which inclined at a rate of 1/96 for a third of a German mile. The wagons were allowed to descend this incline unobstructed. They stationed several men every 50 perches along this declivity, who observed the exact moment by watches indicating the seconds when the train passed by them. They thus ascertained the time which the wagons had to take in running through each of the equidistant spaces. From a series of 14 observations it was shown that during the first seconds of time the load acquired an increasing velocity, but that this soon became invariably constant. Under the stated conditions, the speed amounted to 5 3/4 up to 8½ German miles per hour. Since the resistance of the load only, not of the speed, is determined, the resistance of the air must in this case be the element to arrest greater velocity. This resistance of the air is proportioned not only according to the front surface of the moving object, but also according to the upper surface, which by its movement comes in contact with the air, and its resistance increases according to the square of its speed. That is, if a wagon travels at 2, 3, 4, 5 times greater velocity, the resistance will be 4, 9, 16, 25 times greater. It increases, therefore, by rapid regression, and the velocity produced by the descent is arrested as soon as a certain degree of velocity is reached. Those who are less acquainted with these proportions may imagine that a descent of 1/300 is a precipitous declivity, and therefore it is not superfluous to make the observation that with a 1/300 ascent to every perch, an elevation of half an inch is not attained, and that an unpractised eye would easily be doubtful whether a surface, inclining at a rate of 1/300, ascended or descended on this side or that, and yet this very incline, which the floor of a room may have without being noticed by the occupant, is a steep declivity for the railway business, necessitating double the amount of power and demanding at the same time an increase of running expenses. We intend to illustrate still more closely the efficiency of the locomotive by a definite example. Let us imagine a steam locomotive with cylinders 12 inches in diameter, the pistons of which offer to the steam a surface of 226 2/7 square inches, and this equals a pressure of 13,579 pounds, with an expansion of 60 pounds per square inch. The force then put upon the circumference of the driving wheels is in proportion to that given above as the length of the piston stroke to half the circumference of the wheels, that is, with a 16-inch beat, and driving wheels 5 feet high, it bears a ratio of about 16 to 94 2/7. The force with which the locomotive strives to move itself and the load attached to it amounts therefore to 16/94 2/7 times 13,579, equaling 2,304 pounds. It has been proved by experiment that such a locomotive requires 110 pounds to move itself, which, deducted from the above figures, leave 2,194 pounds, or about 20 hundredweight of drawing power for the load. Yet a part of this must also be deducted in overcoming the internal friction of the machine, which is equally proportional to the mass of the load attached, and therefore cannot be determined once for all. As has been stated, the result of many accurate experiments is that a load on wheels in a horizontal line in good condition may be moved by 1/300 to 1/280, and under less favourable conditions to 1/224 of its own weight. If, then, 2 1/5 hundredweight be deducted from the above 20 hundredweight for the overcoming of the internal resistance of the machine, the power left would suffice to move about 17 4/5 times 280, equalling 4,984 hundredweight. If we deduct from this still the tender of 100 hundredweight, the remainder shows that a locomotive of the given construction on a horizontal line will set in motion the enormous load of a train of wagons weighing 4,884 hundredweight. Next to this maximum load, we have to notice the maximum of speed. The speed depends upon the amount of steam which the machine is able to generate each time. If, after that the steam reaches an expansion of 60 pounds pressure to the square inch, and the train has been put in motion, the generation of steam is suddenly interrupted, the motion itself would decrease at once, and finally stop. For a part of the bulk of the steam escapes at every stroke of the piston. The faster the locomotive travels, the more piston strokes it makes each time. The more steam escapes, and the faster, therefore, must the latter be generated if its effect is to remain the same. The generation of steam, however, depends upon the size of the heated surface in contact with the water contained in the boiler. It is thus determined by the original construction of the machine. If the locomotive is able each time to generate just as much steam as it loses through the piston strokes, the motion will then be constant, all things being equal. If it generates more than the cylinders absorb, the surplus escapes by the safety valve, or is again condensed into water, and this, therefore, determines the maximum speed for each machine, which cannot be exceeded without lightening the load, unless the expansion of steam be increased by loading the valves and thus adding the risk of bursting the boiler. A machine like the one before our mind's eye is constructed so that it generates 1 hour steam from 38 cubic feet of water, with an actual pressure of 60 pounds to the square inch, which under the ordinary pressure of the atmosphere occupies 16,350 cubic feet, and the whole is to issue through the cylinders. We may thus estimate the number of piston strokes, the revolutions of the driving wheels, and thus the distance traversed in 1 hour. The result shows that the greatest working power of our engines is as follows. It moves a load of 4,884 hundredweight on a horizontal way, 5,161 perches, or roundly 2.5 miles, in 1 hour. If the load is lessened, then the pressure on the pistons is lessened, and both pistons and wheels will move faster, that is, a greater distance will be travelled in the same time. The speed thus acquired would be limited in the first place if the heating surface of the boiler were unable to generate as much steam as the cylinders absorb, but in order to avoid danger it is necessary that the motion should be measured by a regulator long before this happened. The greatest speed is made, of course, when the machine with full force descends a down grade, when, for example, it descended the 1/96 grade near Rhine with a speed of 63 3/4 feet per second, or 10 German miles per hour, or again, when the load is reduced to a minimum, namely, when the locomotive goes alone. The distance from Potsdam to Berlin was once traversed in this way in 17.5 minutes, that is, more than 1 German mile had to be travelled in 5 minutes, which, of course, cannot take place without danger, and involves a great destruction of material. Footnote: the greatest speed that can be made on German railways amounts to 90 kilometres, 12 miles, per hour. Strecket. End footnote. End of section 10.